Good morning, children. Welcome to our fourth session based on uncertainty in measurement. Last day we have seen that what are the different units of measurement, how to represent a measured result, that is the scientific representation or scientific notations to represent in the form of n into 10 to the power n, and how to shift the decimal, that also we have seen. Also we had seen that accuracy and precision. Regarding this, I got many queries in the given assignment. Clear for those this is still in a matter of doubt. The measurement could be accurate, could be precise, could be both accurate and precise. That means there could be four different cases. One is accurate and precise both. One is neither accurate nor precise. It is also possible that either only accurate but not precise, or precise but not accurate. To get the accuracy, we should know what is the actual value or the true value of measurement. And precision is the closeness of your own measurement. It is possible that the readings you are taking, these are very close to each other, might be repeating also. So their average value will be very close to individual value. In that case, the reading is precise. It is another case that when we compare the average reading with the true value, if this is also in close agreement, then the reading is accurate too. Secondly, the readings are close enough, means precise, but it is not enough close to the true value. Then the readings would be called precise but not accurate. A third case may arise when the readings are different quite, but their average value is almost close to or exactly close to the true value. Then the readings are not precise among themselves, but the reading is accurate. Because we are considering the average value and the true value. If these are in close agreement, the readings could be accurate. Instead, the readings might not be precise. And the last one, when either you have a long gap between the readings, that is, readings are not precise, not having close proximity, and neither the average reading is close to the true value. The average reading also differs large from the true value, and there is enough gap between the readings. Then this is the case of neither accurate nor precise. The question given, students, please do follow the readings and the compare. Do follow the readings, find the average value, compare the average value with the true value, then you could comment whether it is which case, accurate, precise, neither accurate nor precise, accurate but not precise, or precise but not accurate. Most probably this part is clear. Now coming to today's work. Today we will do uncertainty in measurement, significant figures and the operations on significant figures. Let's first start with uncertainty in measurement. When we measure any of the quantity, say suppose length or volume or any of the thing, we could get some inaccuracy or some uncertainty. That is mainly due to the lack of a particular skill of observer, or it varies from observer to observer. Even for a particular observer, the readings would vary for first observation to second observation to third observation. Then there could be a limitation in measuring instrument, or it is also possible that the skill of observer is very much perfect and there is no limitation, no inadequacy of the measuring equipment, but based on the law of nature there could be some uncertainty. That last part we will deal in structure of atom, particularly for the microparticles. Let's consider these two cases. These are the two major reasons of uncertainty in measurement in the macro world. I have shown one example. It is a burette. A burette is one which is used to measure the volume of acid. These are quite accurate because these are graduated to 1/10 of the decimal place of milliliter scale soil. That means it is able to measure with accuracy 27.3 milliliter, 13.5 milliliter for example. I have taken an example. The starting graduation is 0 and the end one is 50. The volume taken is 12.3. Here in 12.3 milliliter, the digits 1 and 2 are certain, but 0.3, it may be little less than 3 or maybe a little more than 3 also. So therefore the uncertainty lies with plus minus 0.1 because of the place of this is 1/10 of that milliliter. So 1 and 2 are certain, but the first decimal digit, that is 3, is uncertain. Now coming to the significant figures. The total number of digits in a number, including the last uncertain digit, is called significant figures. I am taking the previous example only 12.3, in which 1 and 2 are certain digits, but 3 is uncertain. But including this 3 also, it has 3 significant figures. Now what are the rules to get the significant figures? Check it very carefully because you will find little bit disparity with your previous knowledge. Coming to the first, all non-zero digits and the 0 between two non-zero digits are always significant. For example, 12.5 milliliter. 1, 2 and 5 all are non-zero. We have 3 significant digits here. 14608.7. The 0 lies between two non-zero digits, 6 and 8. Therefore, it has 1, 2, 3, 4, 5 and 6 significant figures. Coming to the second rule. 0 to the left of first non-zero digit is a non-significant one. That means there lies the disparity. 0.000265, we will not consider the zeros to the left of non-zero digit. Significant figures. Coming to the next, 0 to the right of last non-zero digit is significant. That is 6.00 has 3 significant figures. We are including the 2 zeros after the decimal place. 4.600 has 4 significant digits. Though 6.00 is equal to 6, 4.600 is equal to 4.6. There is nothing to be confused, but we are now calculating the number of significant digits. 6.00 will have 3 significant digits. 4.600 will have 4 significant digits. Coming to the rule 4, counting numbers of objects have infinite significant digits because they could have infinite trailing zeros. 12 pen could be 12.0, 12.000 till infinite, any of this. Therefore, when we are calling 12 pens, 48 second has two significant digits, that is 3 and the 0. Now we'll come to the operations of significant figures. We could have addition, subtraction, or we could have division or multiplication. The rule is we have 2 decimal places. The second one we have 1 decimal place, and we have third one 4 decimal places. But since the answer has to be equal to the number having the fewest decimal place, that means only 1. Though altogether it is coming 322.8045, after changing this, we require only 1 decimal place, therefore it will be 322.8, not 8045. Fine, it comes from here. For division and multiplication also exactly same rules to be applied. I have given one example, 6.5 into 12.625. I have 1 decimal place for this one, and we have 625, that is 3 decimal places over the second number. The answer should be 82.0625. Again the same rule, that is one particular decimal place we need to take. So I should have taken 82.0, but the final answer I am showing it is 82.1. Let me explain this. It's obvious that this part will not take place. 82.06, and this, the rightmost number 6, we have to remove based on certain reason. Since only 1 decimal place we have to place, there could be 3 different cases. That is applicable for the digit, rightmost digit, which is to be removed. Why it has to be removed? Because we require only 1 decimal place, that is this, not 2 decimal places. What rules would be there? There could be 3 possibilities. The rightmost digit is either greater than 5. Rightmost digit either be less than 5 or equal to 5. So here 6 is the digit that has to be removed, which is greater than 5. In this case, the preceding number is increased by 1. Fine. So 6 has to be removed. Since 6 is greater than 5, the preceding number 0 would change to 1. Therefore, the total number is actually 82.1. In case when it is less than 5. This is the case where 6 is greater than 5. There could be multiple cases where it is less than 5. Then the preceding number will not change. If it would be 82.03, it would remain as 82.0 because 3 is less than 5. Now, the question is, the number could be equal to 5. If the number is equal to 5, we could have two cases. See the preceding number. If the preceding number is even, that is 73.65, and we want to remove 5. The preceding number is even, so it will not change. It will remain intact if the preceding number is even. 73.65 will remain as 73.6. But if the preceding number is odd, 73.75, the preceding number is odd, therefore it would be increased by 1, and finally this will be 73.8. So this whole is clear why we need to take up to 1 decimal place. In case you have a number which is having 2, 3, 4 numbers in which we have the fewest decimal places 2, round it up to 2, and then apply the removal of the rightmost digit according to greater than 5 or less than 5, or if it is equal to 5 based on even or odd. I'll give some assignments based on this operations and the scientific representations. Only some MCQ I'll give. Thank you.